It's okay that we did not get to that, because this is the type of stuff that you've probably experienced before. Oh, I've got the microphone going, but I don't have it actually being recorded. Or actually right there, I don't have it on. This is the type of stuff that you've probably experienced before, but you might have had questions, but you never really knew where to look for the answers. So if it takes us a little extra time to discuss this, that's okay. Chemistry is a little different. Chemistry, you may have experienced some things in chemistry. Maybe if you were cleaning something, or maybe cleaning products or chemicals. Water, that's not very exciting, so you might not have any experience with that. The thing is, though, there's not as much exposure to chemical reactions than there is to things like light, right? When it comes to light, you guys are exposed to all kinds of different examples of the way light behaves. Visible light, obviously. Colored light, we see that all over the place. As I talked about, your phones are using microwave ovens, right? All that type of stuff you've been able to observe. Even things that you might have seen. I don't know if you've noticed on a hot day, if you look down the road, the shimmering effect that exists above the road. Have you ever noticed that, how above the road it shimmers, right? So we'll be able to explain things like that. Sometimes maybe in the sky you'll see the bright sun, and then you'll see funny little rainbows off to the side. We'll be able to explain and talk about that. So you've experienced that stuff. That's why you have a little more questions on it. Okay, so for today I want to talk about sources of light, how light is produced, and then I want to talk about how light travels, how it behaves, and then in the end we'll make a quick little note about what happens when light encounters an object, and we've actually already discussed that a little bit, but we'll write it down. So sources of light. So objects, which is material, matter that we can encounter, can either be luminous or it can be non-luminous. Luminous simply means it gives off its own light. It is its own light source. So you can see there a candle, a lamp, the sun. We've got all kinds of different luminous objects that we encounter in a day. The fluorescent lamps, the screens. Oh, what did I get? I got an email. The screens on our devices, when we push that button, they become luminous. So something in those screens produces a little bit of light. Non-luminous objects that do not give off their own light. So anything that is not giving off its own light. Like right now, we're not luminous. We're not giving off light in any way. The moon is not luminous. Very often we think the moon is luminous because if it's a full moon, you can see it. It looks like it's giving off light. But where's the light coming from that we see from the moon? Yeah, Justin? From the sun. So we've got a reflection off of the moon's surface, then hitting our eyes. So the moon itself is not luminous, even though we might think it is. All right. So luminous means it gives off its own light. Non-luminous means it doesn't. So let's talk about different types of luminosity, different ways in which things can be luminous. So number one, and actually, you know what? You guys may have already wrote this down in your note if you did the reading I asked you to do the other day. But if you didn't, you can write this down still. Incandescence. Light given off due to high temperature. And I'm going to put some examples down here once we get going. So things that are hot will produce visible light. Really, we're talking about visible light. We're talking about light that we can see. In actual fact, depending on what part of the spectrum you're talking about, would determine whether it's luminous or not. Right? If we're talking about X-rays, not many things are luminous in X-rays. But if we're talking about infrared, heat, a lot of things are luminous in infrared. But we're talking about visible, the light that our eyes are the detectors and we can see it. Incandescent, light given off due to high temperature. Examples of some incandescent objects. Things that are incandescent, giving off light due to high temperature. Yep. A lighter, fire, in other words, right? Fire. Fire. Fire is incandescent. Other incandescent things, things that are giving off light due to their high temperature. What do you think? Where have you seen? Yep. You want to go straight to a nuclear explosion. You like these nuclear explosions, Pat, don't you? You like the big bangs, don't you? Yes, I would say yes. I am not going to write nuclear explosion down as an example, though. But I agree, if I were to ask you for incandescent examples on the test and you were to write nuclear explosion, I would give you a mark. Yep. Yep. The oxyacetylene torch, that itself is also fire. But what happens when you cut the steel? What does the steel do when you cut it with a torch? It turns red hot. That red is light. So hot steel. Now it's interesting because nowadays we light our houses completely different than we did even 7 or 8 years ago. If I were teaching this class 7, 8, 9, 10 years ago, bang, right away I'd get hands up all over the place. They would say to me, yeah? What would they say? No, not an oil lamp. 5 or 10 years ago, we weren't using oil lamps. We got to go back 100 years. But that's fire as well, but I like that. That's funny. Yep. Candles, oh goodness. We're so far off that you guys can't even think of this. This is exciting. Candles they use LEDs and these other type ones, but it doesn't matter. Have you, CFLs? What about the olden days? 5, 6, 7, 8 years ago. What did we do to light our houses? Incandescent light bulbs. Remember those? Does anybody have them still in their house? They're the ones with the filaments in them. You know what I'm talking about? So incandescent light bulbs. Incandescent. And by the way, why do you think they call it incandescent? Incandescent bulbs. They're incandescent bulbs because they're producing their light due to heat. So you plug them into lots of electricity. You let the electricity flow through it like crazy. It goes through the wire, the filament. That gets red hot, like red hot steel, and it even gets white hot, and it gives you some light to work with. What's the issue with incandescent bulbs? Why don't we like the incandescent bulbs anymore? Yep. Yeah, they give off a lot of energy as heat energy. Now, it's interesting. When they were making the changes to those complex fluorescent bulbs, right, the CFLs, complex fluorescent lamps, and when they were switching to LEDs, people who switched them in their houses noticed some of their rooms got a little cold because maybe their furnace didn't like get all the heat into those corners. And the light bulbs were actually producing heat in that room, and so when you turned on the lights at night, it was nice and cozy because the light bulbs were actually heating up the room. So then when they switched to more energy efficient, they found that the rooms were a little cold sometimes because they'd taken away a heat source. All right, so incandescent bulbs. Again, I've been teaching for about 18 years, and when I started teaching right away, people said light bulbs, and I would have wrote light bulbs right there because they were the only bulbs, the only light sources that we had at the time. Okay, there, see? Light bulb. There it is right there. So let's write about another one. 2, fluorescence. Now, in order to show examples of fluorescence, and I'm going to, again, write down examples here. Examples. Actually, I'll write down the examples first, and then I'll try to show you a few things. I don't know whether I don't know whether this is going to work. I tried to show you this yesterday with my UV source, right? So, chemicals that give off light immediately when hit by UV rays. Notice the word says immediately. In other words, I got to have UV rays on it in order to see the light, and if I shut the UV rays off, it stops. So it's immediate. On, UV on, and then it gives off light. Off, it doesn't give off light. The next one I'm going to say that it isn't necessarily immediate, but it lasts longer. And the next one is the glow-in-the-dark material. That's different than this. Fluorescent material is different than glow-in-the-dark material, and I'm going to explain how. So first, let's write down some examples. Well, notice it says fluorescence. So you can see here are fluorescent tubes, fluorescent lamps, all right, which include CFLs, all right, that's not the Canadian Football League. It's a compact fluorescent lamp, which here there is one right there, all right. Now let me show you some other examples of fluorescence and explain to you how it works. Yep, question? Oh, you got an example? What do you got? Sorry? I think I agree with you. Is it blood? No, the blood has to be treated with something. I know there's other bodily fluids that do. If you watch those shows, you know where I'm going. I don't need to explain anymore. See my ickiness? Okay, yeah, that's funny. I'm not going to explain, but there's other fluids that do fluoresce. That's hilarious. I'm not writing that down. And please, on the test, don't put that down. You can just imagine someone's going to be needing one more example. I'm putting it down. No. All right. Okay. No, you're right. That's correct. That would be that's exactly fluorescence. I think the blood, you have to actually mix it with another chemical because and you know what? I'm only getting this from the TV shows because what they'll do is they'll spray down that area with a particular solution and then they'll get that UV light and then they'll see the blood spatter, etc. So I believe that there is another substance that needs to be mixed with it. I'm not sure what it is. Something like that then binds with the blood and then makes it fluoresce. Let me see if I can show you some examples of some fluorescent. What do we got? Fluorescent lamps, CFLs, bodily fluids. No, we're not writing that down. Let me just show you some other things. Now, I tried to show you this yesterday. This is an example of a fluorescent powder, all right? And I've got a couple of examples of it right here, fluorescent powder. And then I also have a fluorescent crayon, and I tried to show you this, but my fluorescent lamp didn't work yesterday. So what I did was I took apart my little old fluorescent lamp, and I tried to connect it to this device. So let's see if it works. So what I have to do is, we tried using this bulb, right? Remember the bulb, the black light bulb didn't work? So what I did was, we had an old fluorescent bulb device that was malfunctioning. So I tried to fix it this morning, and that failed miserably. So what did I do? I tried to sidestep the inner workings of the device, and I tried to give it its own power supply. So this tube here looks a little bit like a fluorescent tube. All right, there's an actual fluorescent tube, and we'll activate that in a moment. And this tube, you'll notice, looks blue, and it doesn't look white. And that's because this tube is just producing the ultraviolet light, all right? This tube also produces the ultraviolet light, but there is a powder on the inside of this glass that then gets activated by the ultraviolet light. And the powder is the substance that's fluorescent. So I have some fluorescent powders that are different colors. And I'm hoping we can see it. So I'm going to dip my finger in it there. You can see it just looks like a regular little powder. And I'm going to take that powder and I'm just going to wipe it on this piece of paper here. And I'm going to close that up. And now we're going to turn off the lights. Quinn, if you could turn that light off there. And now I'm going to attempt to activate this device using this different supply. So you can see there it's glowing, right? And that's producing ultraviolet. And now you can see where I put that powder. Can you see the powder glow there? Can you see it? Okay. Can you see it? Can you see it? Okay. It'll be all over my hands. Okay. You can see it's on my fingers. All right. See that there? All over my hand. So what you can see there is, and you notice I actually got a little bit of powder on the actual tube. See the tube has got some little white flecks on it? That's because I got a little bit of powder on the tube. So what's happening is that powder has the ability to accept that ultraviolet light, and then it produces light that we can see. So it turns the ultraviolet light into visible light. In an actual fluorescent tube, there is powder like this on the inside of the glass. Have you ever broken one of these accidentally? And you notice how there's a powder in there when it comes out? That's the fluorescent powder. The question was, don't they have, there's a little bit of mercury vapor in here, also in here. The mercury vapor helps produce the ultraviolet light. So when you break that, you let a little bit of the mercury vapor out. If you were to inhale that mercury vapor, it's not good for you, it's toxic. Well, it's a heavy metal. It's down near the bottom of our periodic table, and our bodies don't like heavy metals. They tend to accumulate in our brain and cause brain issues in the future. If you were to ingest and inhale a lot of mercury, you'd have brain issues in the future. Okay, so let's take this tube out for a moment, all right? And let's swap in the fluorescent tube. So what this device does is it produces high voltage electricity, which then causes the emission of the ultraviolet light. So I can turn this guy on. And so what's happening in there is it is doing exactly the same as this tube, except on the inner surface of the glass tube is powder like this. And it glows and it gives off light. The neat thing about this source is it actually takes less energy than an incandescent bulb. So it's more energy efficient. But you have to have a box like this in your lamps. And that's what's called the ballast. Have you ever noticed the ballast in there? You might have some people come and they change that electronic piece out. That electronic piece is what is activating that. And you know what? I can get one of those electronic pieces to activate my bulb. That's how I'm going to do that in the future. I'm going to get a ballast from an old fluorescent lamp and I'm going to activate that bulb. Okay, so other places where they might use this. You know, in banks, they have special cash stacks that have been coated with fluorescent dye or a fluorescent powder. You can't see it in the air, but as soon as you've got fluorescent light on it, you can see it. So if someone goes in and does a hold up and wants to get some cash, well, number one, the lady at the till says no problem, and then pushes the button underneath the thing to automatically contact the police, and then she gets the special money out of the special spot and gives it to them, and then when they go out and they count all their money, they're getting covered with this stuff, so if they can be caught quickly enough, they can get their fluorescent light out and they can say, gotcha, you got all the powder from the money and we've tagged all that stuff. So that's the way that works. Other ones you might notice, if you've ever been to an event like a dance or something, sometimes they put a stamp on your wrist, you know what I mean? You've come in the door, that type of thing, to say that you come in. Some of them will put a fluorescent one on, so they do the stamp, you can't see anything, and then you've got to stick a light underneath, and whoop, it glows. Okay, you've been admitted into that particular event. So those are many different ways in which we can use fluorescence. We'll see whether my little pen here works here. My crayon. And actually, you can actually kind of read it a little bit, which is not very fun, but let's see if we can activate it here. See if we can. Yeah, so that you can then, it's because the pencil doesn't stick to the crayon surface. Yeah, that's something a little different, but I don't know if I've ever done that. So let's see what my message is. Huh? No? Yeah, see? No? We're not buying that? All right. That's kind of fun. Okay, so those are examples of fluorescence. Quinn, if you can get the light on the far side off, that'd be great. Or on, that'd be great. Oh, one last one. Shut it down one more time. Sorry. I've got so many things to show you. These are various rocks. There's naturally fluorescent material in various rocks. There's labels underneath them and all that type of stuff. But again, if I were to activate it, you can see there the writing, but that one rock, and I don't know why those others don't fluoresce anymore, but you can see that orange rock. That's just a regular rock, all right? And you can see there that it glows quite orange there. Okay, so you can turn that on. So, fluorescent is when the chemical is hit with ultraviolet light, it glows and gives off this light. It's really kind of glowing. But as soon as I take the energy away, notice it stops. Oh, one last example. If you buy detergent that claims to make your whites whiter, have you ever heard of that? Get such and such detergent. It'll make your whites whiter. What they'll have in that detergent is a fluorescent powder of some sort, or a fluorescent substance. So when you clean your whites, it gets a little bit of this powder on it. Now, under normal circumstances, it may look whitish, but if you go outside into the sun, where there's lots of ultraviolet light, right, because that's how we get burnt, then that fluorescent powder glows white, and it makes the white clothes look whiter. That's often why when you go into, say, a dance event that has black lights, that, you know, if you go in with a shirt like that says lifeguard, that white just gets super bright. Have you ever noticed that before? No, you have never noticed that? Yeah, and that's because they'll often have those pigments in it that will also fluoresce. Okay, that's fun. So let me shut that off, and I just want to get this plug out of the way before I trip over it. Oh, you know what? I'm actually going to leave it here because I want to show you one more thing. Okay, fluorescent. Turn on the ultraviolet source, it glows. Turn off the ultraviolet source, it stops. Got to have the ultraviolet light on it. I'm going to advance to the next one so we can write it, and then I'll take your question. What do you got? If you were to go to great detail, a great effort to, and get the powder, put it on your shirt, it would make it whiter. It would make it whiter. It's a cheat move. It's not that your clothes are any cleaner, you know what I mean? It would just make it appear whiter. Now, this stuff has a green color to it, so this would make it look green. This one is an orange one. I didn't use the orange one. But if you had a white version of it, it would do that. And the difference between the different colors would be different elements used to make those chemicals. Simply different elements are built in. Okay, next. Next, we're going to talk about phosphorescent. Ooh, drop the microphone. That should sound exciting when we put that up online. Big crack on the floor. So, phosphorescence. Phosphorescence is glow-in-the-dark material, and you've all encountered that before. Years ago in my kid's room, I stuck glow-in-the-dark stars on the ceiling, right? That type of stuff. So you turn on the light for a while, turn off the light, and you can see the glow in the dark. Chemicals that give off light when hit by UV rays and stay luminous for long periods of time afterwards. So the difference between fluorescence and phosphorescence is that one keeps going a little bit after the light is off. So the energy is stored. Remember yesterday I talked about electron jumps and how it produces light? With the fluorescent one, the electron jumps happen when they're being hit by the light, and then when you take the light away, they stop. With phosphorescence, the electron jump happens, but then it doesn't fall back down right away. It doesn't jump down, and that's when the light's given off. So it's like they hang out higher up for a little bit of time. So when you take the energy away, the light still keeps coming. So it's like it stores some of that light energy. So glow-in-the-dark materials give off light when hit by UV rays, and they stay luminous for long periods of time. I'm not going to put examples on there because the example is glow-in-the-dark material, and I've already stated glow-in-the-dark there. So these headbands somebody found that were supposed to be glow-in-the-dark. I'm not sure if they are. Can you get the light off there again, Quinn? So what I'm going to do is I'm going to attempt to expose them to some light and see if this happens. Notice it says it's supposed to be ultraviolet. So remember, these are producing a little bit of ultraviolet light to activate the powder, but let's see if they've got enough ultraviolet light to make that glow. And there you can see it's glowing a little bit. You see it glowing? Okay, that's fun. If it is ultraviolet light, I should be able to actually activate it with this lamp. So let's try this. So let's turn this on again. And I got so many switches here to turn on. Too many switches. Where's that switch? There we go. And so let's just lay this on here for a while. You can see here that it's glowing quite nicely because it's being activated. And that actually happens when I'm putting it under the light as well. When I put it under the light, it's already glowing. But why can't we tell that it's glowing? Because there's too bright of a light, so we got to take the light away to see it. So notice this is glowing, but if I take the light away, you'll notice it stays glow in the dark because it stored that energy. So as the ultraviolet light is hitting it, it is glowing, it is storing that energy, but when it's away, it keeps a little bit of that energy, and then that energy is slowly given off. So could you turn the light back on? Awesome. So when we activate a glow-in-the-dark thing, it's already glowing. We just can't see it because it's too bright. Then when we take the light away, we can sense that it's on. Okay? All right. Phosphorescence is glow in the dark. Chemiluminescence. All right, this one's fun. And I'm going to get, again, a demonstration going here for you guys. Sorry? Am I going to glow? No, I am not going to glow. No, but I will show you an example of chemiluminescence. Okay, and I'm just going to get this stuff out of the way as you guys are writing there. When I got to give that a special spot because that's going to break. I'm putting that on my desk. So let me get this out of the way as we're done with it. And I'm going to grab some test tubes. Whoops. All right. Grab the goggles. Oh, my goggles. Oh, right in front of me. Losing my mind. All right. Chemiluminescence, chemical reactions that give off light. When living things produce the chemicals, it's called bioluminescence. That is a freaky picture, isn't it? Look at the freaky eyes on this thing. Anyway, fireflies produce chemicals that, when mixed together in their abdomen, produce a chemiluminescent reaction, and then ultimately give off the light. Why do the bugs do that? I believe it is to attract a mate, in that the rate at which it blinks has meaning to other bugs. So how quickly the blinking is happening is a communication mechanism, I believe, to other bugs. Yep.
Do you know fireflies only live for 48 hours?
I did not know that. So they wanna communicate so that they can procreate. Okay. All right. So we've seen these, right? We've seen these before, all kinds of them. And these are these glow sticks that you can then have the connectors and make a necklace out of it and all that type of good stuff. So if I shut this light off, and let's get the other light off there, for a moment, and I do this type of thing, right? I break that thing that's in there, and oh, this might not work. I was hoping to use this as a demonstration. It is working, but my plan was to get the two liquids out and put them in test tubes and separate them. The issue that I'm concerned about is it looks like the glass piece runs all the way along here, so that's going to be difficult to do. Let me do another one here. What's happening here? Oh, that guy looks almost like a dud, and it's not doing anything. Oh, we're getting some blue action there. Okay, so let's get the lights back on. And it would not be comfortable. Okay, so here's my plan. And who knows whether this is going to work or not. My plan is to take my, my school tool knife, which is why I have it, because it is a tool that I use as a science teacher. And I'm going to cut this off, to cut the end off. Oh, but the glass is right there. So this is not going to work. Well, because I wanted to collect the liquid. Nothing's coming out. Not even close. What if I were to... The glass, what happens is, let me explain. Inside these tubes are two different chemicals, and they have to be separate from each other. In other words, in a non-reacted state. Then, and one of them is on the outside, in between the plastic and a little thin piece of glass. And on the inside is a tube that's made of glass that contains the second chemical. When you break the glass, you mix the two chemicals together, all right? Now, in the larger glow, you know, like, you know, those big ones that you can wear around your neck, like a big stick that helps you, like, they're separated quite well, so I can cut it and pour the liquid out. What I wanted to do was I wanted to get the liquid out that's on the outside, and I wanted to separate it from the liquid that's on the inside, put them in two test tubes, and then show that when I mix it in a test tube, you can actually see the light being produced. But the problem is, I can't get the, I wonder if I cut it like this. If I cut it like that. There's the glass piece. I can sense the glass piece with my cutting tool. And there's a little bit of liquid there, but there's no way for me to catch that liquid. There's about a drop of it. Like there's a drop of liquid there. What do I do with a drop? Oh, it must be an acetate. That's fun. I can smell it. Hold on one second. I got a backup plan. If there is only a couple of drops, then I can't do it in a test tube. But if I do it on a watch plate, I might be able to mix those liquids in a very small amount. So let's try cutting this down the edge a little more. See if we can get it to work. Cut. So I've got the one liquid. It's all over them. Oh. Did anybody hear what happened there? I broke the glass. So I just have a chemical mess going on here is what I've got at this point. This is just an absolute mess. So I broke the glass. I've now got it all over my hands. So I'm able to get the glass piece out. So I've now got the glass piece out. But now I've got some of the chemical that's on the inside. Let's get the lights off there. Let's see what we got. It's not there. You can see on my hand, there's a little bit of something. Oh, look at the back of my hand here. So I've got some on my finger. What if I touch that finger with the other one? So what if I touch here? There you can see it's kind of activated. You see how it's activating there? So I tried to get some that was out of the middle onto the watch glass. As I was cutting, I had the outside stuff on my fingers. And now there I've mixed it together, and there's the chemical reaction happening. You can see it here. It's starting to happen on the outside there. But again, you got to get that chemical to come out of the glass. So this didn't work too bad, but it's not bad, but it's not great. This isn't hot in any way, so it's not burning me, but it's definitely not a chemical that I don't think I want to leave on my hands for too long. So I'm just going to do a wash there. You can get the lights back on there quick. Okay. So again, in those glow sticks, the reason you've got to bend them is you're breaking the container on the inside so that the two chemicals can mix and then produce a chemical reaction. Yep. Yeah, go ahead quickly. Okay, so let's move on to the next one. Triboluminescence. Whoops, sorry, click. Triboluminescence. And I actually stopped at the gas station this morning to see if I could get some wintergreen mints, but they didn't have any Lifesaver Wintergreen Mints, because I don't know if you've heard of this one. There are certain crystals that exist that when those crystals are broken or rub up against each other very quickly, they will produce a little bit of light. And that's what triboluminescence is. And it used to be that they used to say if you had a wintergreen Lifesaver mint and you put it in your mouth and you broke it and you kind of left your mouth open, you might be able to see a little spark or a little bit of light. And I've done this with many classes where we turned the lights off and everybody looked in each other's mouths as they were trying to chew on these things. We never saw a spark once. But unfortunately, I don't have any mints. I'm sorry. I went to get some this morning and I didn't get any. Yep. No, flint and steel is a friction scenario, so that's incandescence because it's getting hot. You see what I mean? So it's not a crystal. It's the friction of the two substances rubbing together and getting hot. Okay. So triboluminescence, not very exciting. Certain crystals glow when put under some stress. Electrical discharge, and that's essentially sparks. Lightning, sparks, all that type of stuff. Oh, there's glass in there. Do I want to put that in the broken glass container? No, I'm going to leave that in there. Different gases glow different colors, and that's example like neon lights, right? So if you've ever, if you see the open and closed signs for various stores, if they're those tubes, right? Those are examples of neon lights, and which are examples of electrical discharge. Now that's all we're going to, well, actually there's a couple more at the very end. But there is another source that has recently been discovered. It's kind of a silly little source. We'd never use it really for anything. And it has to do with sound waves being put through liquids. There's a funny phenomenon that if you put high intensity sound waves through a liquid, it forms little bubbles. And then these little bubbles collapse on themselves very forcefully. And as they collapse on themselves, they give off a little bit of light. So they're calling it sonoluminescence or something. But I just recently read about that 2 or 3 days ago in a science kind of magazine thing. So I'm not going to count that one yet until I've seen more evidence of it. Yep. You can, but I'm going to put the brakes on the rest. So if you're bored with my little speeches, we're not going to have a revolving door of bathroom goers. Go ahead. Okay, so electric discharge. Let's now talk a little bit about LEDs. And as you guys know, LEDs are very important these days. So I'm going to show you a little bit about these things. LEDs are an example of, they're like an electric discharge, but they're in a very controlled situation. So within the LED, there is a small little circuit, all right? And so these two materials are brought very close together, and as the electricity goes through that little circuit, it causes, again, electrons to jump, and when you get electrons jumping, you get light. And years ago, LEDs were very rare, right? I would have one little LED to show the kids, and woo, it was exciting. Again, back, maybe 10 years ago. Then we had LED Christmas lamps, and in actual fact, now the TVs, the light at the back tend to be LEDs. So we have LEDs everywhere. You now can buy LEDs that go into the bulbs in replacement of your wasteful fluorescent bulbs, and they produce lots of light, all right? The trick with LEDs is that they don't need very much electricity. Here I've got 3 little LEDs that run on a couple of batteries. This used to be a nice little snowman, but I tore it apart so I could find the LEDs. And you can see there, these LEDs, they turn on and off. So if you had it covering like a snowman, if you get the light off there for a minute, Quinn, I'll just explain this. If you had it covering a snowman, you could get all these different colors of the rainbow by mixing the different colors together. And so there you can see we can get blue. Oh, and there's a little bit of magenta, and a little bit of yellow, a little bit of green, and a little bit of purple. And as the lights vary, right, they give you the different types of colors. So you can get the light back on. But LEDs, they don't waste heat or energy. They don't use any mercury, and they last a long time. They used to be expensive, but now they're cheap. They make them by the piles, right? So like anything else, things start out expensive when they're first invented, and then as they kind of perfect the manufacturing process, they can get cheap. All right. So we've got LEDs all over the place. Stands for a light emitting diode. And then finally, one last source before we talk about how light travels. Again, you might be thinking, oh man, we're doing a lot of notes today, and we are. I had planned on doing a little more yesterday, but we talked a lot about the spectrum. We will be getting to labs on Monday. So we will be doing a lab on Monday on reflection. So I apologize. It's one of those days where we're just kind of getting some information down. All right. Yeah, they don't waste energy as heat. These things never get hot, right? The LED itself does not get hot. Now, you might notice, I don't know if you've noticed, if you've ever changed one of those fancy LED bulbs, that if you grab it, it's got some heat to it, right? You know, the ones that you screw into a regular old light bulb? And that's because there has to be a device in there that takes 120 volts and turns it down to about 3 volts. Because these things only need 3 volts to run. But our lamps and our plugs all have 120 volts. So there has to be an electronic device that turns the 120 volts down to 3 volts. And that uses energy. And that's why they do have a little bit of heat associated with them, because you've got to change that voltage level. We could actually run all of those bulbs on a couple of batteries, and it would run. But people like those old sockets. They want to be able to put things in those old light sockets without having to change all the sockets out. One last source of light that we're going to talk about. We're not going to watch the lasers video, so just relax, because I've got to talk about the way it travels. But the last one we're going to talk about are lasers. Laser light. Very specific form of light. And I've got Sheldon standing right in the way where I want to fire my laser, so I'm going to move Sheldon.
Shooting the laser?
Oh, Sheldon's stuck. Get out of the way there. Okay. So lasers are a very important source of light. A laser light is made by a special tube, all right? It stands for light amplification by stimulated emission of radiation. So don't worry about what those words mean. It means that it's amplified light. And again, it has everything to do with the core of the laser, all right? There are many different types of lasers. Years ago, the only lasers that we had these were the lasers that we had years ago. These big beasts. They were awesome. They still work. You might think, wow, this is awesome. You should be able to like cut through steel with this thing. You can't. In actual fact, this laser, which is a little tiny laser level that you buy from Mastercraft, right? A little tiny laser. Actually, let me get that out of the way. There it is there. This laser is actually more powerful than this laser. This laser is probably 25 years old. I'll plug it in anyway and show you what it looks like. It's got a great big power supply. You need to plug it into 120 volts. Let's get the lights off there, Quinn, for a minute. So if I turn that laser on and I turn the switch on and I open the little window on the end, and why am I not getting laser light? Am I? Oh, there we go. So you can see there down at the end, we're getting some laser light there. That's awesome right there. Actually, there's something in the way because it shouldn't be making that funny look. But if I then take the laser level and I put that out there, you can see there that's an even better and intense beam. So again, technology has advanced to the point where it is very bright and intense. So I'm going to get that out of the way, and I'm going to leave that laser running there for a minute and get this guy out of the way. So lasers are pretty cool. They're a special type of light. When we have a regular white light bulb, it has all the colors of the rainbow in it, all of them. And so it's made up of many, many different colors. But if I have a laser, that's made up of just one color. It's a perfect, pure color. It's very bright, and the color's the same. The beam also stays the same. Now, I wanted to show you something. I'll get my light on here. And I thought I'd brought it out here. I got to find some equipment right here. Okay. Lasers are really cool. Lasers can do something called interference. So what I have here, all right, is a special plate that we use in physics. And this special plate has slits in it. And if we put a laser through these slits, I can get an interesting pattern. So I'm going to take this and I'm going to put the laser through a slit here. And actually, you know what? I need some light to see this. This is terrible. I need just a little bit of light because I got to see where the slit is. I'm going to use this one. I'm going to put this one here. Okay, come on. Where are you? There we go. See there? So I put it through a slit. And you can see it's caused the beam to kind of separate. And it almost looks like it's a bunch of beams. Let me see if I can find a different slit. Come on, different slit. That's a different one. Oh, it disappeared. There. You can see the separation is different. So you might think that it's like blocking it, like a shadow, but it's definitely not a shadow. Now, it's what's called an interference pattern. So what I have here in my hand are these little tips that used to go on these little lasers. About 7 or 8 years ago, these little cheap lasers that you could get at the dollar store, and you should probably still can, right? And if you push the button, you could get a little laser light, and everybody was going like this and putting it on their foreheads, and everybody was doing, and it's like every second kid at school had one, which was really annoying because we had a laser ban, because these, like I said, are more powerful than those bigger ones. So in theory, if you held somebody down and you held that into their eye, you could burn their retina and cause some eye damage. You'd have to hold it there for like 4 minutes, right? But you could have some damage. You wouldn't have any damage if it like went, oh, I was hitting the eye with a laser. Am I blind? No, you wouldn't be. If it just kind of went, whoop, you wouldn't be. You'd have to hold it there for 4 or 5 minutes. But because the potential was there, we said no lasers. So it was awesome. I'd go around school and I'd say, hey, give me that laser. Yes, confiscate another laser. Hey, give me that laser. Yeah, another laser. Awesome. My lab was full of lasers. It was great. I didn't have to buy any because everybody had them. But what they came with were these little caps that you'd screw on the front. Now, in these little caps is a diffraction grating like this, which isn't as boring as this one. This one makes it separate into a couple of dots, but these diffraction gratings have a special design that allows you to do, and now I'm going to show you what it looks like. So if I take this and I put it on the front here, and can I put it on the front? What's going on here? Why am I not getting that laser on the spot? See, I'm struggling. Oh. See, the reason is that I can't put it right on the front of this one. Oh, see there? Oh, look at it. Makes a pattern. Oh, see it? And you know what, guys? I do. I care. I'm one of those teachers. I care about you guys. All right? Don't ever think that sometimes when I get a little upset, because I care. All right. So that's kind of silly. Let me show you another one here. Oh, this is not lined up very well. Oh, there's a good one. Honey. Now, I don't know if we can see it, but there's supposed to be a second pattern to the side. You see there's a dim pattern right there to the right? It's a very dim version of it. And that's because this pattern will repeat just like the dots repeated. And that's because it's made from a diffraction grating. So because of the way this light behaves, I'll do one more. Hey, woo! All right, so you can see here, there's the repeating pattern to the right. Can you see the repeating pattern there right over Nolan's head there? And there's another repeating pattern off to the left. Now I put it on the paper. So this pattern is really very much like the dot pattern, except it's a more complex version, okay? All right. Uses of lasers. Uses of lasers. Does anybody know uses of lasers except this silliness? By the way, this silliness doesn't count. Pat, what do you got? Ah, so like being able to know that you're pointed in a straight line. It's like a laser sight. All right, I like that. Laser sight. Again, Pat, very much military. I'm very concerned. You don't own guns, do you, Pat? Don't even answer that question. Laser sight. A laser sight. Excellent. How about something non-shooting and non-blowing up? What do you got? Ah, for cutting. 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 Excellent. Those are typically what are called CO2 lasers, and you can't see them. They're invisible, but they're super hot, and they can be used for cutting. Yep. Laser eye surgery, it uses cutting, but I like that. Eye surgery. Surgery. I have no idea how to spell surgery. Yep. Hair trimming? You mean to remove the hair so it doesn't grow back? Like if you've got an unwanted hairy thing that you want to be less hairy? I guess so. I don't know how to describe that. Laser hair removal? Laser hair removal. All right. I'm not writing laser hair removal, but that's correct. I like it. You know what? I've even heard some of these laser clinics that say they can stop your smoking with lasers. I have no idea how that works. I have no idea how that works. What do they do as soon as you bring a cigarette up? Ow! Ah! Okay, well, I'm going to quit smoking. I don't know. I can't even imagine how that. By the way, I'm going to go for some old technology here. Actually, I will bring it up to speed. 10 years ago, I would say CD player. But then I had to say a DVD player. But now what is the latest technology? A Blu-ray player? I'm telling them uses of lasers that 10 years ago I used to say a CD player. But they have no idea what that is. Oh, there's a CD player right there. I'm going retro. CD player. We're going retro today. CD player.
Impressive. Logan.
Logan?
And Tyson.
Tyson. Logan and Tyson.
Logan and Tyson.
Right up front.
That's the two.
Logan and Tyson.
Thank you, sir.
Yep, no problem. Okay, we're going to continue on now at this point. Try not to bump my cart there, guys, when you go by. All right. What's that? Yep, that's correct. Lasers are everywhere these days. And you know what? Years ago when I started teaching, it was very rare to see a laser. All right? Okay, let's keep going. Now we're going to talk about how light travels. Very fast. Yes, that's good, isn't it? Shouldn't light travel at the speed of light? How else is it going to travel? But then it's not light anymore. Then it's lost its ability to be light once it stops. It can only exist at the speed of light. Yes? How do you measure the speed of light? Oh my goodness. That is a very long story, how they've measured it. Question? You can take any speed and convert it into a time as long as you give it a certain distance to travel. All right? So you can, if you specify a particular distance, then you can describe any particular speed as a time. That's why when we travel somewhere, we very often don't talk about how far it is. We often talk about how long it takes to get there, right? Somebody says, hey, how far is it from here to Strathroy? That's about 45 minutes, right? And that's not a distance, that's a time, right? So yes, there's a special type of length that's called Planck length. And if you apply the speed of light to that, you can get a distance. And that's probably what you may have read in a thing. But we can talk about it in terms of speed. Yep.
Doesn't it take like 8.5 minutes for light to reach Earth?
Yes, that's in one of my slides. What? Slow down, man. Are you reading ahead? Oh, okay. For about 8.5 minutes. That's the distance effect. Correct. Okay, let me keep going, and then we can talk about this stuff. Jeez. So it travels very fast, and it travels in straight line. We call that, the technical term for straight line travel is called rectilinear propagation. All right, so it means it travels in a linear sense, and propagation just means to travel. Okay, how fast does it go? It goes much faster than sound. So what I want to do now in a little discussion is talk about how light travels a lot faster than sound. And I'm sure you've experienced this kind of delay effect when it comes to the fact that you hear it and then you see it. Sorry, that's backwards. You see it and then you hear it. Like lightning, right? You see the lightning and then you hear the thunder, because the light from the lightning gets to us very quickly, and then you hear the thunder. You might even notice it also at maybe like a baseball game if you're sitting way back, and if you didn't have a lot of people there, you'd see the guy swing, and then crack, you'd hear it a little bit later because it takes time for the sound to catch up to the light. All right. You may even notice it. Out just on our soccer field. Someone way across the field does something like at a track meet. You see the poof, and then you hear the crack, and then you see the. I got it backwards. You see it first, then you hear it. You see the poof, and then you hear the crack a little later on. Right. Echoes. Whenever you encounter an echo, that's that delay of that sound, right? That delay of that sound. So we see an event almost instantaneously, and then the sound catches up, and we hear the event later. Any explosion from a great distance. You want to crank it up and be nuclear as well, like Pat? All right. We'll turn everything. We'll have a nuclear reference to everything. My next slide has a couple of examples, but I think, actually, yeah, we are going to write those down. We are going to write those down. I know it's one of those days. I apologize. We're going to get to the lab on Monday. So lightning. After we see the lightning strike, it takes time to hear the thunder. Typically, what's the rule? What's the old wives' tale rule? Yep. Seconds. And then and then how far in what unit? Kilometers? Some people say that. I've even heard people say that's the distance in miles, right? So if you see the lightning, you go 1, 2, 3 miles away or 3 kilometers away. In actual fact, that's not true. Every second, it actually only travels about 1/3 of a kilometer, right? It travels 300 meters. So 3 seconds is actually just 1 kilometer. So it's much closer than you think. But sound can also be carried by the wind. So it doesn't work perfectly for storms. It's not a bad little thing. But let's say it makes the lightning and the sound is made in the air, and then the wind is blowing the air away from you, then it's going to take a lot longer for that sound to get to you. But if the wind is blowing the air towards you, it's going to get there much quicker because it's actually moving the thing that's carrying the sound. So it's not a bad little thing, but it's probably not correct. It's probably not true in kilometers because the sound travels a little faster than that. It takes the sun's light 8 minutes to reach the earth. Oh, don't worry about how far is the sun from the earth. I used to do that calculation. With another class, but I'm not going to do that here. That's stating it in time, right? That's light minutes. That's light minutes. That's correct. That would be a light minute. Okay. So let's now talk about the rectilinear propagation. Now, at this point, I would be drawing these shadows. I'm now going to switch to some paper for you guys to see what I'm drawing so that you can draw it as well. So I'm going to change some technology around here. And you guys can draw that up. And I'm going to then, or you can write it down, and then I'm going to show you how we're going to draw it up. And I'm actually just kind of getting ready because I'm going to be doing more of this drawing later on. Let me just get it set. So at this point, you are going to each need a ruler. So you can send some people up to grab some rulers. Now, look at these rulers here. Brand new, right, still in the package. So we've got to get into them somehow. How the heck am I going to get into these things? I thought there would be a flap on here. Is there no flap? Oh, there it is. On the bottom, there's a flap on the bottom. So when you come up, you can take the ruler out, all right? In the end, we can throw this in the garbage. Please, never grab my rulers like this. They're never designed to be grabbed like this. Don't do that. They will break. So don't do that. Never go like this. Don't do that. Don't do this. Because then it's not straight anymore. All right? So if you need a ruler, come on up and grab a ruler. But please, don't destroy my rulers. The flap is at the very bottom. We can throw it in the garbage later on. Don't worry about throwing the plastic in the garbage right now. So just like my styluses, don't wreck my styluses and don't wreck my rulers and give them back to me.
Never said not to throw.
Don't throw the rulers. Don't throw the rulers. I need a ruler. Somebody took the one I already took the bottom off of. Okay. All right, and now I'm going to switch over to some different technology here. Oh, input. Where's the input button? Can I switch? Okay, take a look at what we got going here. So here I've got some technology that is going to allow me to, see, isn't that fun? Woo! That is going to allow me to show you what's going on. So at this point, I'm going to grab a pencil. And on that, there was a little candle. So let's just write down a little dot here. Let me just put it right here. A little dot right there. And that's going to be the light source. All right, so you can put down light source. And then I'm going to put the circle. And I'm going to put the circle out here. Okay? And by the way, this is a small light source. So please put the word small. And by the way, light sources produce rays of light that go off in all directions, like the sun. Now, you can put those on the back side, but then I'm going to use my ruler on the front side. So those are called rays. I'm going to put some arrows on them. So I'm going to label one of these. These are called rays. So those are rays of light. And therefore, this is a ray diagram. Are we okay so far? Now I'm going to take my ruler and I'm going to draw a ray that comes from my source and just grazes the top of the circle. See how I'm just touching the top of the circle right there? So I want it to just graze the top of the circle. And look at, I did a terrible job at that. Do it better than me. See what I did? I'm now going to put an arrow on that because whenever we draw ray diagrams, we always put arrows to represent where the light is going. And now I'm going to draw a ray that grazes the bottom side. And these two rays are very important. By the way, I'm going to put a little note here. Note. 2 rays are always needed to locate an optical effect. So if I'm wanting to locate something in optics, I always need 2 rays. That's how I find it. So in through here, it's all light. This is what we would say is light. It's light over here. But over here, it's dark. Oops, you can't see that. Light. You still can't see it. Light. Up there is light, and down here is dark. That dark part is the shadow. All right? The dark part we call the umbra. The umbra. The umbra is the dark part of a shadow. Okay? I want to draw one more. I've got 2 more minutes. I can do it. Down in the bottom, I want you to put below it, I want you to put a larger light source. In this case, I'm going to put a bulb. That's a light bulb. See my light bulb? Is it? Okay. This is a large light source. This is a large light source. It's big, as opposed to the little tiny light source. Put the object. This time, starting from the bottom of the light, I want you to put a line that hits the top of the object and a line that hits the bottom of the object. And then from the top of the light, I want you to do the same thing. A line that hits the bottom and the line that hits the top. Okay? When you have a big light source, like my projector, and I put an object in front of it, look at how the shadow is fuzzy. Do you see how the shadow is fuzzy? All right? This image right here represents that fuzzy shadow. This is dark. And again, it's called the umbra. So this is dark, and again, it's called the umbra. I apologize that it's harder to see that one. Up here is light. Yep.
Mr. Sanders, is Jocelyn Lynette in class?
Yes, she is.
See her in the office for a moment, please.
Yep, you can. In between, all right? It's not light or dark, but in between, we call that the penumbra. The penumbra. All right? If we have large light sources, we have fuzzy shadows. If we have small light sources, we have, and I want you to stick this in here somewhere, sharp shadows. And that's where we're going to stop today. All right? The existence of shadows is evidence of the fact that light travels in a straight line. All right. Don't take my rulers. The plastic stuff can go in the garbage. I have a garbage pail by the door here if you need to get rid of the plastic stuff. Don't snap my rulers. Brand new shiny rulers. Thank you.
Lisa McGregor, Emily Lyon, Vera Leckie, Kelly Levine, Rachel Kelly, Trent Rickey, Sam Shade, Mason